Hello, I'm JW. This time we're going to have a look at those four things as on the title. So volts, amps, resistance and power. So all of these things are closely related, and it happens that if you can find out at least two of those things, you can actually calculate the other two. And this is actually very useful because a lot of equipment doesn't actually have all of those four listed on there, and it may be useful to know these things in many situations. And certainly for things like, say, heating equipment, if you know, say, the resistance, you can then work out the power for various voltages. And again, if you happen to come along to it and it just told you what the actual rating was, then you can work out the resistance and do a quick check there to see if it's within the kind of expected range. So this will be a fairly brief overview in terms of what these units actually are. Obviously we're not going into huge depth because that could take literally hours, but this is more just a view of what they actually are, how they're related, and how you can actually use these things for real installations. So let's first of all have a look at voltage. And you've probably seen voltage on many things. You've got, say, 240 volts for the mains, or it might be 120 volts if you live in certain other countries. And then you've got things like 12 volts, would be a car battery. And then sort of your 1.5 volts might be one of those AA batteries. And of course there's all kinds of different levels there. If you happen to climb up a pylon or something in the UK, then the small ones would have 11,000 volts on there. And of course the ones with a made of metal would have considerably higher. And generally the case that voltage can be thought of as electrical pressure, and the higher the voltage, then the higher the pressure or the force that's going to be involved there. Now voltage is always measured between 2 points, because essentially it's a difference between 2 points. Usually that's going to be the ground and whatever you're testing, certainly in the case of main circuits. But if voltage was sort of considered to be pressure, then that's a reasonable sort of comparison. And just as with pressure, say on water pressure or whatever, if the voltage is higher, that means there's a lot more force behind it. So if you opened a tap and there was a massive pressure behind it, a huge amount of water is going to come out of there. But on the other hand, if there was a tiny pressure or none at all, then the water would only just basically crawl out of there. And the same sort of thing applies with electricity, in that if you have a higher voltage for any kind of given piece of equipment, if you turn up the voltage, then a lot more electricity is going to be flowing through there. Now, speaking of how much electricity is flowing through there, this is the current. Current is measured in amps, and it's usually given the symbol A. So you might have, say, 5 amps, or you can just sort of put 5A. And the current is really how much electricity is actually flowing through there. So for example, a 5 amp circuit might be, say, typically used for lighting, and that's a fairly moderate amount of power. But if you had a huge electric shower, you might require, say, a 45 amp circuit. The shower is considerably more powerful, therefore it needs a lot more electricity to actually make the thing operate correctly. And of course there's all kinds of other ratings in between. Generally in a domestic situation you're not going to be seeing much above the 45 amps range, but of course for other places all kinds of ratings above that are easily obtained and regularly used. So voltage is the amount of pressure involved, so higher voltage means higher pressure or a lot more force behind the electricity. This is why things like climbing up a pylon is so dangerous. So you've got this massive voltage here, say 11,000 volts, or in some cases 435,000 volts. And the higher the voltage, the more current is going to go through any particular item. So if a person climbed up a pylon and grabbed hold of the 435,000 volt wires, the amount of current that we would shove through their body would be massive, and it would probably have to cause instant death. But on the other hand, if you went and licked the terminals of a 1.5 volt battery, not a great deal is going to happen because the voltage is so tiny, there's not a lot of force behind it, so the amount of current that's going to flow is going to be extremely small. So it's all kind of relative. You increase the voltage, that generally increases the current as well. Now for any particular item, say a person or a piece of equipment, it has a property which is called resistance. And resistance, as the name suggests, is the amount of resistance it puts up to current actually going through there. So if something has a high resistance, then it's actually quite difficult for electricity to get through there. And conversely, if it has a low resistance, then it's very easy for considerable amounts of electricity to get through. So if you look at the previous items here, if you had a fixed voltage, say we picked the mains voltage 240 volts, if we apply 240 volts to something which has a low resistance, then because it's very easy for the electricity to go through there, then you'll find that the current that goes through there is actually fairly high, because it's very easy for the electricity to flow through. However, if we take the 240 volts again and you apply that to something with a high resistance, then the current in this case will actually be fairly low, simply because it's much more difficult to get the electricity through there. So if you've got a high resistance, the current is inevitably going to be low for any fixed voltage, and if the resistance is very low, and then for the same voltage you're going to get a much higher current, simply because it's easier to push the electricity through. And you think of resistance, if it was, say, a pipe, that a low resistance would be a large pipe, sort of wide open there, so easily for electricity to go straight through. But a high resistance could be a pipe which had a narrow section inside. So even though you might be trying to shove the electricity through here, this very thin section here, you're not going to get a great deal of stuff going through there. So of course the amount of current, or the amount of flow through here, is going to be significantly less. Now for any given voltage that's going to be the case, but if you increase the voltage, because we're basically then putting more force coming along here, giving it a lot more shove along the wires, then the current will increase regardless of what the resistance is. But in both cases, if the voltage is the same and you've got two resistances, then the lower resistance, it's always going to be much easier to get that through there. Let's say if you turn up the voltage, then the current will also increase, simply because you're putting more force behind it. So there's your high voltage, you're going to get a bit more coming out the other end. But of course on this one, if you turn up the voltage, then you're going to get a lot more coming out as well. Now all those things are clearly related, so this is how they actually work. So you've got voltage, and then you have current, which we use the symbol for I, and then resistance is the symbol for R there. And voltage is normally in volts, current is all there is in amps, and resistance, of course, is measured in ohms usually. So for any given voltage, and if you know one of the other two, then you can actually calculate the one that's missing. So if, for example, we had 240 volts, say, on the mains there, we know that the resistance of something, like, say, a heating element, was 20 ohms. Then to calculate what the current would be in that situation, then it's one divided by the other. And if we actually draw a line in here, voltage over resistance, so it's 240 over 20, so 240 divided by 20, and that will give us the missing one, and of course the answer in that case is 12. And of course, because it's current, it's going to be 12 amps. So you had a heating element, you measure resistance of 20 ohms, put 240 volts across the ends of it, then 12 amps is going to flow through that particular heating element. Now for any piece of equipment, the resistance is generally not going to change because it's a fixed property of the, say, heating element or whatever. And if you just refer back here, it's just a question of how much restriction there is in the actual wires. So that's a physical property of the heating element or whatever. It's not something that's actually going to change. However, what can change is the voltage you've connected to it. So in the case of the heating element there, instead of it might be rated for 240 volts, but if for some reason you decided that was inappropriate and you connected it to a 480 volt supply instead, then resistance is still the same. It's still going to be 20 ohms, because say that's just a property of the wire and how long it is and so on. But in this case, the current's not going to be 12 amps anymore. It's going to be 480 divided by 20. So that gives us a current of 24 amps rather than 12. And again, if you reduce the voltage, the current would reduce. So these two things are directly related. Increasing the amount of voltage or increasing the amount of pressure there is going to increase the amount of electricity that goes through, or the amount of current that flows through. And say generally the resistance isn't going to change, because say the only way to change that, say on a heating element, would be to make the heating element longer or shorter, or make it out of a different material or something, which clearly is not going to magically happen unless you start dismantling it. So resistance in electrical terms is generally a fixed item, but of course the voltage you apply to it can certainly be changed, and in doing so you're then going to actually change the current that flows through. Now this can of course work in the other way as well, so just look for the other page, so volts, current and resistance. So if you know any two, you can find out the other one. So as you saw there, current is voltage divided by the resistance. If you wanted to know what the resistance was, it's voltage divided by the current. So if we say had the 240 volts again, and we could measure the current, and it turned out it was going to be 12 amps, which is the one we had before, and 240 divided by 12 is 20, which is that 20 ohms that we had on the previous page. And again, that will work for any values just the same. And then the other one is if you inexplicably knew the current and the resistance, but you didn't know the voltage, then you can work it out. So it's just the current multiplied by the resistance. So if we again take the two here, that will be the current of 12 amps multiplied by the resistance, which was 20 ohms. And of course the result is 240, as we saw previously. However, in the real world situation, it's highly implausible you're not going to know the voltage, because the voltage is the one thing that's really easy to measure. So we just get a multimeter in the two wires and place them on the terminals, there's the voltage. So although you can do it that way, in real installations that's never going to happen, because the voltage is always going to be the thing you can quickly and easily measure. Resistance you can measure directly as well, but we need to do that when the power is disconnected, so that may not be totally practical. You can measure current on main circuits, but there are certain issues in doing that, particularly if you've got to start opening the circuit and inserting a meter in a series with it, which is generally not recommended. But those are those three values, so it's just a question of the amount of pressure, how much electricity is going through, and how difficult or easy it is for the electricity to get through the particular piece of material you've got. Now the fourth thing here, which we're just going to cover, is power. And that's generally expressed in watts. Now power in watts is all related to those other three values we saw previously, and you've probably seen on the side of heating elements sort of things like 1000 watts, or say an old type incandescent light bulb might be 100 watts, or a new LED one might only be 5 watts. And this is all about the amount of power that's being dissipated by the piece of equipment. Most power ends up as heat. Some of it might come off as light in the case of a lamp or whatever, but ultimately most power ends up being dissipated as heat. And if you had to say a motor, the power will be coming out as sort of mechanical energy, and heat as well, because everything heats up when you put power through it. And these are all related to those previous three values, and you've probably seen on the side of appliances and ovens and whatever else, they have a certain rating in watts. Now if you have a look at that previous example there, where we had that heating element, which we had the 20 ohm element and its proper voltage of 240 volts. Of course it came out as 12 amps. Now the way to work out power is very similar. It's the power, which we're saying watts there at the top, or P for power, and the other two values underneath are the current, which we've seen before, and the voltage, which I think we've seen before as well. So if you want to find out the power of a particular item, it's the current multiplied by the voltage. So if you use that example of that heating element we had earlier, we know that the current was 12 amps, and of course we know that the voltage was 240. So the power then will be the current, which is 12, and the voltage was 240. So 12 multiplied by 240 gives us a result of 2,880, and 2,880 watts. Now that's a fairly powerful heating element, and it's normally the case if you've got watts in the thousands of figures to, instead of putting 2,880 watts, it's quite common to change that to kilowatts, which is essentially just dividing by 1,000. So in this case, that will be 2.88 kilowatts. And that might be a fairly typical heating element, say a immersion heater or electric kettle in your kitchen. Now, just as with the other two, if you increase the voltage to a particular piece of equipment, that's going to increase the power as well, because it's the two multiplied together. So if you increase this figure here to some other value, then of course the power is going to increase as well. So any power rating that's displayed on a piece piece of equipment is only correct when it's actually used at the correct voltage. So in this case, 2.88 kilowatts when it's supplied with 240 volts. And a side effect of this, because it's the current multiplied by the voltage, if you increase the voltage, say from 240 say to 480, as we saw previously, if you increase the voltage to 480, the resistance of the item stays the same, but the current increases as well. So if we turn up the voltage here to 480, it will be 480 here. Of course, the current isn't 12 anymore because, as we saw on the previous example, it's now up to 24 because increasing the voltage always increases the current as well. So it's 480 times 24. So the power now is dramatically more. Although we've doubled the voltage, the power hasn't actually gone up by a factor of 2, it's actually gone up by a factor of 4. So this is why it's essential that pieces of equipment are supplied with the correct voltage all the time, because if they're not, it's not just a question of it's slightly more power, it's actually 4 times the amount of power. And in the case of this heating element, it's not 2.88 kilowatts anymore, it's actually 11,520 watts, or if you want to put it the other way, it's 11.52 kilowatts. And pretty obviously a device that's designed to put out about 2 or 3 kilowatts, suddenly putting out nearly 12, it's going to overheat and melt and destroy itself pretty much instantaneously. So voltage increasing, it's not just a doubling of the voltage, doubles the actual power, it's actually a factor of 4. Now, just as with the other one, if you know any 2 of these, you can find out what the other one is. So, as we saw there, if you don't know the power, then it's the current multiplied by the voltage, and that's probably the most likely scenario because, again, you can measure both of those fairly easily. However, you can also do it so that if you know what the power is and the voltage, you can then work out what current is going through there. And that can be useful in situations where the appliance doesn't actually mark on it what current it actually requires. So it might say, for example, it's 2,400 watts, say electric kettle or something, and you know what the voltage is because you can easily measure it, or it's in your house, so it's going to be the 240. So then the current, 2,400 divided by 240 volts, and the answer in this case is 10 amps. So electric kettle uses 10 amps, so you need to make sure the wiring for that could take at least 10 amps, and you would probably use either a 10 amp fuse or 13 amp fuse for that. You can also do it like this, so if you inexplicably knew the power of something and also how much current it took, you could then work out what the voltage was. That's fairly unlikely, because again the voltage is always the one that's easy to find out and measure, but nevertheless if you did somehow find the power and the current but not the voltage, then you can just divide one by the other to find out what the voltage is. Now if you put those two things together, so we had voltage, current and resistance, and then we had power, current and voltage. It should be fairly clear that if you know any 2 of these things, you can actually work out what the other 2 are as well. So if you knew, say, what the voltage and the current were of these 2, you can then work out what the resistance is here. And because you know what the voltage and the current is, you can put those in here and find out what the power is. However, if you knew inexplicably what the resistance and the voltage were, but didn't know what the current was, you can find out what the current is over this side, because that's just voltage divided by resistance. You can then put the current in here, and you already know the voltage, so voltage is there. Multiply the 2 together, and you get the power. And if you knew the power and the voltage, say you had an electric shower that was, say, 8.5 kilowatts, and it was at 240 volts, you can use this side to find out what the current is, because that's just power divided by the voltage. And then once you've got the current here and the voltage, you can put those in over here, and then you can work out the resistance of the heating element inside. So these 2 things are really the only ones you need to remember. There is a kind of a wheel-shaped thing which has all of these all worked out in this sort of ridiculously complicated fashion, but you don't need to remember all that. These are the 2. The same, you may have to just do things a couple of times there, but you can easily find all of the things if you know any 2 of them. And in theory, you could say take the I here, and because you know that I is obviously V over I, you could put that in there, then it's V squared and so on, but that's all far too complicated and rather difficult. Just remember those two, and that pretty much covers the whole situation. And you may see these things sometimes drawn with a triangle shape around like that. But essentially it's just the three things there, VIR and PIV, so voltage, current, resistance and power. So a little recap there then. Voltage is the amount of pressure or the amount of force that's involved, so high voltage means there's a lot more shove behind it, and higher voltage also means higher current, because again you're shoving a lot more force behind it, so a lot more current is actually going to flow, more electricity is going to move past a particular point. Resistance is the property of, say, a heating element or other piece of equipment, and it's how easy or difficult it is for the current or electricity to flow through there. So high resistance will mean it's quite difficult to force electricity through there, and low resistance means it's really easy. So for any particular voltage, if you're going to have a fixed voltage, if you've got a high resistance, then there's going to be a small amount of electricity through because it's quite difficult to get it through there. But the same voltage on a low resistance, you're going to get a load of electricity through because it's just much easier for it to go through there. And those three are related by volts, amps and resistance. And then power, which is the amount of energy of a particular item, is measured in watts, and that's power is equal to current multiplied by the voltage. So if you turn up the voltage, inevitably you're going to be turning up the current as well because of the previous things we saw there. So on this one it might be 218 kilowatts at the proper voltage of 240. If you double the voltage, you're actually quadrupling the power, because if you increase the voltage you're also increasing the current at the same time. And then it's PIV, and if you know both of these things, VIR and PIV, then you can easily calculate any two from any of the other two. So it doesn't matter which two you've got, you can always find out the other two just using those two things there. So that's a fairly brief look at those four items, so voltage, current, resistance and power. And the important thing to remember is they're all closely related, and if you change any one of them, which is generally going to be the voltage, then you're going to be changing the other things as well. So turning up the voltage is definitely going to increase the current in most cases, and it's certainly going to increase the power as well, which is why things like kettles and electric showers or whatever are designed to work at one particular voltage only, and if you try and use them at other voltages, well, they're not going to work as intended, and in some cases they could set on fire or not heat up the water at all. Now all of that is basically correct for anything which is a resistive load, and that's generally things like heating elements or older type light bulbs or that kind of thing. However, it is not the case for modern electronic items, and you can identify these because the power supply for them will generally say on it something like operates between 100 and 250 volts. Those are actually designed in such a way that they can work over a very wide voltage range, basically because they're electronic, they're not a fixed resistance inside. It's basically electronic circuits which will vary their characteristics depending on the voltage applied to them, so it doesn't work for things like that. And the other thing to be wary of is things like electric motors, which are heavily magnetic in construction. And again, that's a different situation altogether. But for basic simple things where you're just applying a voltage to a particular item, then that does work. And in, say, things like heating elements and things, it's exactly what you would expect. Now in later videos we'll have a look at motors and things as well, but until next time, thanks for watching.